Hey everyone, and welcome. So, what if you could spend the exact same dollar twice? I mean, in the real world with a physical bill, that's just impossible. But online? In the digital world? This was the fundamental problem that haunted every single attempt to create digital money for decades. We're talking about the double spending problem, and today we're going to break down exactly how solving it created true digital scarcity for the very first time. Welcome to CodeAccessHub. Our whole mission here is to make even the most complex tech easy to understand for absolutely everyone. So whether you're a seasoned developer or you're just curious about what's coming next, you are in the right place. We're here to break down the tough stuff into clear, practical explainers. Okay, just think about this for a second. Really, what if you could just copy and paste a digital dollar, just like you would a photo or a text file? What would that dollar actually be worth? Yeah, you guessed it. Absolutely nothing. This one simple question gets right to the very core of the challenge that stumped some of the brightest minds in cryptography for years. And that brings us to the main villain of our story today, double spending. It is the ultimate Achilles heel for any digital cash system. I mean, if the same digital coin can be spent in two different places at the same time, it's really no different from just printing counterfeit cash. It creates money out of thin air, and worse, it completely shatters any trust in the system. The currency just becomes worthless. Now, long before Bitcoin ever came onto the scene, brilliant people were already trying to crack this nut. These early pioneers, they really laid the essential groundwork, but every single one of them ran into the exact same critical roadblock. So let's take a look at how they first tried to solve it. Back in the late 80s, you had David Chaum's DigiCash, which used some really clever cryptography to keep things private. Then, in '96, eGold came along and tried a different approach, backing their digital currency with actual physical gold. And fast forward to 2004, a name you might recognize, Hal Finney, created something called reusable proofs of work, or RPOW. It was a direct forerunner to Bitcoin's system. Each of these was a huge step forward, but they all shared the same fatal weakness. And that weakness, it was centralization. Every single one of these early systems, at its heart, had to rely on a central server or some single authority to check transactions and prevent double spending. And that creates what we call a single point of failure, right? If that one central server gets hacked or it goes down, or maybe it's just controlled by someone you can't trust, the whole system just collapses. The real holy grail was to build a decentralized system where no one person or company was in charge. So to make that happen, to achieve trust without a central leader, computer scientists had to solve this famous, almost mythical thought experiment. And this wasn't just about writing code. It was about figuring out how to coordinate a complex action when you literally can't trust everyone you're working with. It's called the Byzantine Generals Problem. Picture this. You've got a group of generals surrounding a city. They all have to agree unanimously to either attack at the same time or retreat at the same time. The catch? They can only communicate by sending messengers back and forth. And here's the twist, some of those generals might be traitors, sending fake messages to sabotage the whole plan. So the question is, how do the loyal generals agree on a single unified plan? This is the exact same problem a decentralized network faces. How do all the computers agree on the true history of transactions when some of them might be trying to cheat? And the solution, laid out in Satoshi Nakamoto's Bitcoin white paper, was just ingenious. It's called proof of work. Instead of trusting messages or people, the network trusts raw computational power. You see, miners all compete to solve an incredibly hard math puzzle. The winner of that race gets the right to add the next block of transactions to the public ledger, what we call the blockchain. Now here's the crucial part. To go back and change history, to double spend your money, an attacker would have to resolve that puzzle and the puzzles for every single block that came after it, all while outpacing the entire rest of the honest network. It's not impossible, but it is incredibly difficult and outrageously expensive. It makes cheating a really, really bad financial decision. But, solving that original problem didn't just end the story. Our villain, double spending, didn't just give up and disappear. Oh no. It just got smarter. It evolved. Attackers found new, clever ways to try and cheat the system, often by exploiting the very nature of how a decentralized network works. So attackers developed new strategies. There's a race attack, which is basically a sprint. You send two conflicting payments out at the same time and just hope the merchant accepts yours before the network figures it out and rejects it. The Finney attack is way more devious. For this one, the attacker has to be a miner. They secretly mine a block that includes a transaction sending their own coins back to themselves. Then they go spend those same coins with a merchant. And right after the merchant says okay, they release their secret block to the network, which suddenly invalidates the payment they just made. It's a classic bait and switch. And then, well, then there's the ultimate threat, the 51% attack. And this chart really shows you everything you need to know. If one person, or one group, manages to get control of more than half, 51% of the network's total computing power, they basically become the new boss. They can mine blocks faster than everyone else combined. This means they can just ignore the honest chain and build their own fraudulent version where they get to spend their coins again and again and again. And look, this is not just some scary thought experiment. It's happened. In 2018, the cryptocurrency Bitcoin Gold was hit with a massive 51% attack. The thieves successfully double spent over $18 million worth of the currency. Real money just gone. And it didn't stop there. In 2020, Ethereum Classic suffered not one, but multiple 51% attacks, with attackers getting away with more than $1.6 million. These real-world examples are a stark reminder that for smaller networks, without that massive decentralized computing power, this threat is very, very real. Okay, so with all these threats out there, how in the world do you stay safe? Well, here's the good news. The network itself has powerful built-in defenses. And as a user, you also have tools and strategies to protect yourself from becoming a victim. All right, rule number 1, and if you take away nothing else, remember this. Wait for confirmations. Never, ever consider a payment final the second it shows up. It's also super important to use reputable exchanges and honestly stick to the biggest, most secure networks like Bitcoin and Ethereum. The amount of computing power on those networks makes a 51% attack practically unthinkable today. And finally, you can actually keep an eye on a network's health yourself. A sudden, big drop in its hash rate can be a red flag that it's more vulnerable. And this table here illustrates that point perfectly. A transaction with 0 or just 1 confirmation, meaning it's in the newest block, is still pretty risky. You can think of it like a check that hasn't cleared yet. For most of your everyday stuff, waiting for about 3 to 6 confirmations is generally considered very secure. But if you're talking about a large, high-value transfer, you might want to wait for 12 or even more, just to be absolutely certain that transaction is locked in and irreversible. You know, this whole battle to prevent double spending is really a constant arms race. As the attackers get smarter, the defenders have to get smarter too. So let's take a quick look at how the next generation of blockchain tech is building even stronger shields. The future here is filled with some incredible innovation. We're seeing hybrid models that combine the best parts of proof of work and another system called proof of stake. You've got layer 2 solutions like the Lightning Network that move tons of small transactions off the main chain for speed and lower risk. And then there's advanced cryptography like zero-knowledge proofs, which are adding new layers of security and privacy that honestly used to feel like science fiction. And all of this brings us to one final, really crucial question. The invention of blockchain was revolutionary because it solved the double spending problem and created true, verifiable digital scarcity. But as technology keeps evolving, this cat-and-mouse game between building security and trying to break it, well, it continues. And as this technology gets woven deeper into our world, this fundamental battle for trust is only going to intensify. Hey, if you found this breakdown useful and you want to get your head around more of the incredible tech that's shaping our future, make sure you subscribe to CodeAccessHub for more explainers just like this one. Thanks so much for watching.